All right, so here we are. We're going to talk about data management this week, and briefly, the presentation here is actually pretty brief. I'm not going to spend a lot of time on this, but what I do want to do is kind of go over, because the book can be very explanatory. It can have a lot of information in it, and I want you to just focus on what these different methodologies are for looking at the data itself and pulling something out of it. So I'll kind of walk through the key points that I want you to know for the week. Okay, so data management. We have all that data. What do we do with it? In the big field of analytics, there's a lot of things going on. There's a lot of new technologies, a lot of new algorithms and such coming into play. But 99% of what you need is going to be out of a few simple methods. So that's what we're going to show you this week, just to give you a flavor how to actually do some of these things. Now, like I said in the intro, or in the week 5 intro, there isn't something that says, when you get this, you do that. You just got to have these things in your toolbox and kind of be creative with when you want to employ them and when you want to use each one of them. A lot of what you're doing when you do analysis is just basic math, right? You're going to have to look at what you see in front of you and say, what are some averages? Know what different averages mean. Be able to use matrices, stuff that you took probably in your math classes, to do value comparisons, computations across that. Linear programming, the basic optimization kind of linear programming that we talked about earlier in one of the examples with the P8s for Australia. That's a method to achieve best outcome at lowest maximize your profit, lower your cost, whatever, in a mathematical model whose requirements are represented by the linear relationships. And then just accounting principles. Understanding accounting principles is key to just being able to do good analysis. All of these things I've got on this chart, you just need to, a lot of this stuff is just using math correctly and being able to understand how the math relates to the problem that's at hand. Statistics is the same way. So a lot of the questions are going to be, what's the best likelihood of making this decision, or where should we go for this? Sometimes it's just basic statistics, quantify the amount of variation. You figure out what the measures of confidence are and what you're trying to do. Polling data, big thing in statistics, calculate the expected standard deviation, so you kind of can make some assumptions about what you should move forward with in terms of your customer approval, in terms of if you're going to allocate some certain security assets to certain fields. Understand statistically what your best probability is for achieving the goal that you want. So statistics and math will help you in terms of a lot of the just overall modeling that you need to do with data and understand what to do with it. Probability then is a third key. So you've got understand how to craft probability questions in a way that's going to represent the problem at hand. So there's independent kind of true, false kinds of things like I got there. Probability of A or B, which is the probability of A plus probability of B minus the probability that both of them occur. Being able to chart that out in terms of making assessments in terms of all the data that you're seeing is important to understand just basic probability language and being able to understand the relationship between different outcomes and the probabilities of those two outcomes. Now we get into data science. Data science says, all right, well now, once we've got all this data, there's some things that we can do with it that might be a little bit more, give us some insights that maybe we haven't thought through before. And so we're going to talk through some of these things. Data Smart, they use basically spreadsheets to get at this stuff, which is fine. It's just absolutely fine. I mean, a lot of data that you have will just be spreadsheet level. Not everything is in big data. But these same techniques work across large data sets as well. And that's what we want to be able to look at. The question is, what kind of problem are you looking at? And that's where we're going to look at some of these key different ones and see what kinds of problems they might solve for us. Most of your high-level analysis can be done using these kinds of formulas. It's not appropriate for simulation. And when you get into some of the bigger statistical programming or larger data sets, a language like R is what you want to use to get into those. But for now, this helps us understand some of the key methods. So the big one is clustering. When do you use clustering? Clustering is for market segmentation. So it's huge within the commercial space. This is like the big thing that everyone does for commercials, for marketing, those kinds of things. It allows you to go through, it gathers up a bunch of objects, separates them into small groups of similar objects. So you can do some exploratory data mining. Forces you to tease out some qualities about the data. So if you need to break it up into some groups, you have a large mapped set of data and you need to break out some groups, you tease out some qualities that say, well, this has this and belongs in that group and this, and you let the math sort of create these clusters by distancing itself, each object from each other, to see which ones have certain affinities. And the book will go into all that with you, but basically you create these clusters, decide what makes sense, decide what you want to cluster, determine what each of the clusters means, and identify how far from each one the cluster is going to be. So you'll do this a lot in socioeconomic modeling. If you're looking at a population, trying to understand the security ramifications of different types of people, different tribes, different kinds of things like that, what their activities are going to be. If you want to understand inequality about a large data set like that, clustering can be very. If you're doing maintenance on aircraft, if you're doing on servicing, anything that describes how things are being done, that's where your clustering is going to come into play. Naive Bayes is another one your book's going to go into, and you should really sort of understand this one. In big data searches, it was one of the major means for culling out useful data from all the noise. And what it really helps you do is just create knowledge based not only on the presence of some of the values, but on the relationships to each other. So if there's noise in there, it's going to sort of fall out as not playing as important. If you're looking at, let's say, internet searches or internet communications, you might look at the probability of something as the probability of having certain words and not being with stuff from a certain set, or you look at the probability of having a certain set of words and then with that set being within a certain set of communications from certain people. That will tell you certain things about who is communicating, what kinds of things they're communicating, and then what the probability is that they're having some certain relationships with those people. So this is one of those things that can be a very important algorithm, especially looking at some of the communications and comment stuff that you use. Optimization is really about applying scarce resources. So we talked about linear programming a little bit. There's also A-star graph traversal algorithms, which basically say you map all the data and then you sort of start with what you think is an optimum, and then you fan out to any of the adjacent data sets to see if there's something better. And then when you find one better, you move on to the next one. You sort of follow this path. Not always perfect. There's always the chance that there could be some optimal out there. But what this does is when you can organize data into a sort of a general flow, then you can use these kinds of A-star algorithms to really optimize within those data sets, whatever you're looking for. Model randomness is another one that you come out of optimization. So what you do is you introduce randomness into it. So think about the static simulation we did last week or a couple weeks ago, where you kind of just knew all the probabilities for the models and the attacks and you played it all out. Monte Carlo simulation, what you do is you look at the curve of probabilities, let's say from a standard deviation perspective, and you start to map in there. Here's the probabilities that this would happen. Here's the probabilities of this launch being able to take place. Here's the probabilities of this hit. And then you play those over top of each other. And so you execute that simulation multiple times with many variables along that sort of curve of a Monte Carlo arrangement. So that's what Monte Carlo does. And it gives you a little better understanding on average being the key word there, of what you're going to come up with, or what happens when different conditions are present. Network graphs and community detection. This is real important for decisions where you're going to be looking at what relationships build over time. So it's really another clustering approach, but unlike k-means, this is based strictly on relationships that you might have with each other. So when you're looking at, from a security standpoint, individuals and their relationships, what their communications look like, you can use network graphs to really understand who's maximizing here and who's not making connections. Where do we not see connections? Where do we see connections? A lot of the discussion that you hear nowadays on these 3 hot queries coming out of the NSA stuff, on phone calls to discover terrorist cells, that's all coming out of this kind of detection. So network graphs I can lay out to say, hey, I'm going out of the country with this hop, and I'm coming back in the country with this hop. That all feeds into this. This also drives what you would hear when you hear about neural nets. That's essentially what we're doing here. We're taking a lot of data and we're building vectors based on relationships. That if this has a relationship, then I'm going to build a vector out there, and I'm going to build another vector. and it winds up building sort of the paths of the way that the mind thinks in terms of relationships and paths and memories and such. So a lot of that's going to come out of network graphs. This is an important one to understand. Regression analysis is used pretty extensively anytime you're doing optimization or prediction or prognostics or forecasting. We'll talk about forecasting just in a little bit, but regression basically says you turn past data into a formula or set of rules that can predict future behavior. So you look at everything that happened in the past and you say, well, it happened with these kinds of patterns. Now let's go ahead and do some linear regression that says, well, in the future we expect that it'll probably, move out in these directions a little bit, but these are probably the best recommendations in terms of forecasting what's going to happen in the future. So anybody who uses an account to buy something that's in your inventory is going to get this kind of data for you. And that's the good thing about this, is it can be applied just across any data that you got. If you can track anything on anyone, you can do regression analysis on it. After creating a model, you always want to test it, make sure it's accurate. And then you want to basically refine it as you go, understand how to modify it so you can minimize your false positives so you're not wasting a bunch of resources on things that aren't true, and minimize your false negatives so you don't have, missed opportunities out there. Good to recognize that you're going to spend your money better on good data than on clever models, and that's where one of these things comes in. If you can get really good data, regression analysis can help you get in the direction pretty fast. The corollary of regression analysis is really just forecasting. That's what we're doing here. We're saying it's about some variable over time. We're looking at past experiences, curves, and setting, etc. You're trying to defeat uncertainty. Now, uncertainty, you don't have a time machine, so you can't defeat it, but you need to manage it. And what forecasting does is allows you to sort of quantify prediction intervals. So exponential smoothing over time series allows you to give them predictions that say we'll have a pretty good idea of some sort of demand next year, and then the year after that a little less, but we'll be able to put a case out there, and then so you have this expansion as it goes forward. And that's kind of what forecasting is doing for you. It's really focused on non-technical kinds of activities and what can you forecast in terms of the level of activity. It's a poor long-term predictor of behavioral patterns. And I want to make this point because this is important. All these models have to be continually updated, and the reason is because people don't think in straight lines. People react to the environment around them. So you may forecast that certain behavior is going to increase 20% each year, but after it reaches a saturation point, people find something new to do and it changes. It's the old Malthusian principle, thrown on its head, that we were going to overpopulate the earth. People do act differently when the conditions change around them. So that's why we always got to be going back and readdressing these models and looking at them again. Circles of probability take that to its conclusion, where you say instead of predicting single occurrences, you're saying, all right, look, I got a 25% probability this is going to happen, 25 this is going to happen, and then you go out and this is really important for like allocating resources. So if you say we've got we can only protect this certain amount of a coastline, where do we want to allocate our resources based on the best probability of what's going to happen? You forecast what their intentions are. You forecast then what they're going to where they're going to apply, and you do that. It's a scarce resource modeling technique. They do it with insurance companies all the time. I mean, it's exactly what you do. You decide exactly how much to invest in insurance based on the likelihood of any of these things happening, both 3, 4, 5 steps out. And then finally, you just got to manage your outliers. You got some things that are going to happen, important events. Outliers can point to important things like fraud. They can point to things like anomalous behavior that in itself might be something to track only because it's outside of the model. And so, what you do is you detect those basically by degree counts and by the k distance, doing your k-means algorithms. So you can either choose to ignore it based on what you're looking at and what the question is, or you can choose to pay attention to outliers based on maybe that's what you're actually looking for. Who doesn't fit the pattern here, And then conclusion, like I said, there's a lot of responsibility that comes with this. Be aware of the 3 things you need to watch out for. Use the right tool for the right question. Always keep it as simple as possible. Think about how fast does it really need to be. Don't go overboard about that. And don't be so in love with the math you forget the reason for the question. So always keep focused on the problem at hand and make sure you're picking the right tool to do the right job.